In this video, we'll focus on how to calculate hydrostatic force from the pressure. Okay. Now let's see the figure here. We have a tank to retain some kind of fluid, let's say water. We can see two sides of the tank. So these are the two sides of the tank. And let's assume the tank is very deep because we are not concerned about the bottom of the tank, only the two sides of the tank for this example. Now the purpose of the hydrostatic force calculation is to design the structures. We want to design how thick this wall should be, what materials we should use, and what kind of cross-section is suitable to safely retain the fluid inside the tank. So that's the purpose of the calculation. Now, how to calculate the force? How to calculate the hydrostatic force in this example? For that, we need to know what the pressure is. So what is the pressure applied by the fluid on the wall? So that's what we need to know. Once we know the pressure, then we can calculate force by multiplying it with the area, right? So for that reason, you want to calculate the pressure. One thing to remember is pressure is different at different locations. So pressure at somewhere here is different than somewhere here. Okay, so pressure is different at different location. Now, how do we calculate the pressure at different points? To find this answer, let's create a free body diagram of a small column of water. So let's cut a small column of water here. Okay, so maybe from here. So we just cut the small portion here and make a free body diagram. Okay, so let me cut it here. So we cut it here and make a free body diagram. And we are talking about the hydrostatic. That means water is not moving, right? So this column of water is supported by the force from different directions, right? And that's what we make the free body diagram here. We all know that the free body diagram is a diagram with replacement of the supports on the body when it was in its original position. So this column of the water, small column of the water, is supported from three different directions in this two-dimensional plane, from x direction, two sides, and from the bottom. At the top, it is atmospheric pressure exposed to atmosphere, so we don't need to write because there was no force. Actually, there was the atmospheric pressure, but we just ignored it. Okay. Now let's consider some very important point. First, all the forces are acting perpendicular to its original supports. Okay, so all the forces are perpendicular, so there is no inclined force like this, right? That means there is no shear force. All the forces are perpendicular. Second, we can see that from the right, force is equal to the left hand side force. In this example, we have the this force acting towards right and this force acting towards left. They should be equal and opposite, right? Because there is no inclined force. That means the horizontal forces should be equal and opposite. If that is not the case, then this column of water would be moving in that direction. If the force, this side of force is bigger, then water would be moving in this direction, which is not the case because this is the hydrostatic, which means water is not moving. So from horizontal direction, there is no movement, so forces from the left and right are equal. And from the vertical direction, there is a weight of water, which is W, and the upward force acting on this body of water. So these are the two forces. Okay, so weight of water and upward pressure on that column of water. Now, what is the weight of water? Weight is volume times density times G, right? So area, so whatever the bottom area is, it maybe rectangular or circular, whatever the area, times the height. So up to here, this is the height So area times height gives us the volume times density times G is the weight of water. So that is the force acting downward. And what is upward? Upward force has to be the same, right? And that's why the pressure is force divided by area, and that is rho g h times A divided by area, and that is the pressure. So at any point, the pressure is rho g times h. Now let's see how the pressure variation occurs at different surfaces. For the tank here, we have two sides of the tank and bottom of the tank. When we design this structure, we need to know what forces are acting on the side of the tank and what forces are acting on the bottom of the tank. Now, at the bottom of the tank, the height of water is same at all different points. Okay, everywhere the height is the same. So you measure the height at this point, which is h, or at this point, or at this point. So h is the same, and that's why the pressure is uniformly distributed. Okay, so uniformly distributed pressure, and the value of the pressure is rho z h, and rho g is also gamma. Okay, and that's why gamma h. Okay, so at the bottom, gamma h. And because this is the uniformly distributed, the resultant force acts through the centroid of this force distribution, which is at the center. Now, the next one is on the sides. The height of water starts at 0. So at the top, height of water is 0, and the pressure is also 0. Whereas at the bottom, the pressure is rho g h or gamma h. So as you go down, the pressure increases, and that's why the pressure looks triangular with 0 at the top and gamma h at the bottom. And for this, the force will not act on the centroid of the surface. Yes, because you see this is the triangular force, so force will not act at the centroid of the surface, but at the centroid of the force diagram. Now let's make it a little bit more formal. Assume there is a plane surface immersed in water. Okay, so this is a plane surface, and we want to measure the pressure. So what is pressure? The pressure is density times g times height of water. So density of water times g times height, and that height depends on where we measure the pressure. Okay, so we measure the pressure at this location, then height would be only up to that point. But if you measure the pressure at the bottom, the height is all the way to that point. So that's why the pressure diagram looks the triangular, and it shows the distribution of pressure over the immersed surface. So what is the distribution of pressure can be seen from this pressure diagram. Now let's look at pressure variation on vertical plane surfaces. Okay, so we first consider about the vertical surface. Okay, that is perpendicular to the water surface, and we are immersing this plane surface here, and we can immerse this plane surface in three different ways. So you can encounter three different ways of vertical plane surfaces immersed in water. The first one is total immersion like this. Okay, and this top of the plane is at the water surface level. Second is like this here. The top is immersed below the water surface with the height of h1. So up to this point, so if you look at the first figure here, at the top pressure is 0, whereas at this figure, even at the top of the surface, you get rho g h as the pressure. So even though the distribution of pressure is triangular, the actual pressure acting on this surface is trapezoidal because it doesn't start with 0, but it starts with rho g h1 at here, and then it goes on increasing and at the bottom it becomes rho g h2. So the figure of pressure distribution is trapezoidal like this, right? And the last one is the vertical plane surface, which is partially submerged, only partially immersed, which means only pressure starts from this point, right? So above that point, the pressure is 0, and below that point, we see the increase in pressure. Now let's look at when the surface is inclined like this. The magnitude of the pressure does not change, okay, even it is inclined. So the pressure at this point, regardless of the inclination of this surface, pressure is rho g h. Okay, so there is no change on the pressure at this point. But that pressure applies, the direction of the application of pressure changes because the pressure applies perpendicular to the surface. Because that's the important point in hydrostatic, because there is no shear force acting. That means the pressure has to be perpendicular. Okay, so if the surface is like this, pressure acts 90 degree, or surface is like this, again pressure acts at 90 degree. In terms of magnitude, it doesn't make a difference. Okay, you just measure the vertical distance, vertical height from that point to the water surface, and you multiply with rho z to get the pressure at that point. So at the top, the pressure is rho g h1. Similarly, the bottom of the surface, which is h2 unit below the water surface. So regardless of its orientation, the pressure it experiences is rho g times h2. So at this point, the pressure is rho g h2, but the direction of the pressure is not horizontal, but perpendicular to this surface, and that is rho g h2. So you can see that the pressure distribution triangle is rotated, and that's the only difference. Now for the second figure, the surface is horizontal. You can see the surface is horizontal, which means the entire surface is exactly h unit below the water surface. Okay, so everywhere, at every point, the height of water is h. This means at all points of the surface, the pressure has to be the same, which is rho g h. Okay, so everywhere same. All right, so let's move on to the next. Now let's talk about the stratified liquid. Because different liquids have different density, the pressure by these liquids on the immersed bodies will also be different. In this example, we have H1 depth of oil. Okay, so H1 depth of oil above H2 deep water. Because the density of oil is less, oil floats on the water, right? So that's why you have two different stratified liquids. Now, let's look at the pressure diagram due to the oil only, and it will be triangular as regular, so it starts at 0 at the surface and rho 1 times g times h1. Okay, rho 1 is the density of oil times g times h1, and that is the pressure here. Okay, so rho 1 g h1 up to that point. Now below the interface, we need to be a little bit more careful. We cannot just say rho 1 times g times h1 plus h2, right? Because the liquids are different and the density are different. So below the oil water interface, the pressure due to water should be rho 2 times g times h2. Okay, so if you look at only the pressure due to water, that will be rho 2, that is the density of water, times g times h2. So at any point, rho 2 times g times h2. But also we need to add the pressure due to oil, right? So that pressure is already here, so we need to add that pressure below. So we just add the constant pressure due to oil, because wherever you go from this oil water interface, uh, the weight of oil remains the same, right? So up to this point, this is the maximum point with the highest weight of oil, and below that point the weight of oil remains the same. It doesn't increase after that point. So that's why we have the constant pressure due to oil and the linearly increasing pressure due to water. So the pressure diagram looks a little bit complicated, but you can see if you can divide in the multiple parts, it's not that complicated, not complex. So first, you just made a rho g H1 from the first fluid, and then you just add the constant part to the bottom, and for the next fluid you just start at 0 from that point and make the triangular pressure diagram as before. Now we can calculate the hydrostatic force on a body. Okay, so once we know this pressure distribution diagram, we can extend it to calculate the force on the entire area, which could be gate or dam surface. Okay, so let's uh, see how to calculate the force on this, let's say a gate. We know the force is area times pressure, and we can apply the same here. We have this a triangular load applied on this one, and we just want to extend it to the entire area. In this example, because the pressure is uniformly varied, right? So 0 at the top and rho g has at the bottom. We calculate the average pressure from top to the bottom. So average at the bottom is rho g h, and at the top it is 0. So average pressure is 0 plus rho g h divided by 2. If the pressure is not 0, as in the previous example, then we just use whatever the pressure at the top is. So rho g h1 plus rho g h2 divided by 2. Okay, so we just take the average. So if the pressure diagram is like this, then we take the average of this and this value and so on. And in this example, the top is 0, so rho g h plus 0 divided by 2. That is the pressure, and now once we know the pressure, we multiply with the area. So area, whatever the width is, so B times H gives us the area. So the pressure, sorry, hydrostatic force is pressure times area, which is rho g H times area. So average pressure, which is half of rho g H times area, is the pressure. So the hydrostatic pressure is written as hydrostatic force is written as F equals to rho g Hg times area. Okay, Hg is the vertical distance of surface centroid from the water level. So it's very important to remember here. This Hg is the centroid of the surface. Okay, so that's the a very important point to remember. Hg is the H by 2.